Welcome to this highly technical professional deep dive. Today, our mission is to present a geomechanical blueprint. We're going to translate, those academic geological classifications into actual engineering realities for crushing plant configurations.
Right, because, well, a geological label on a map is really just a starting point.
Exactly. And to do this properly, we're going to walk you through a virtual slide deck today, detailing rock behavior, wear costs, and crusher mechanics.
Yeah, we have to establish a baseline first. A label like Cretaceous limestone, it isn't just academic. It dictates exactly how that rock will behave against a crusher liner.
And that behavior comes down to four main drivers, right?
Spot on. You have crushability, which is the work index, or WE. Then abrasiveness, the AI. And finally, fracture behavior and gradation. Those four metrics are everything.
Got it. So moving to the next slide, we reimagine the Earth as an industrial processing plant.
I love this model. It's the rock cycle engine. So igneous rocks, those are your furnace product.
Born from cooling magma, right?
Exactly. Then you have sedimentary rocks, which we call the volume kings. They form from erosion and cementation over time. And finally, the metamorphic rocks.
The solid state transformers.
Yeah, baked by intense heat and pressure underground, but, without ever fully melting.
It's basically a manufacturing supply chain where nothing is permanent. A granite intrusion weathers down into sandstone, and then extreme pressure bakes that into quartzite.
Exactly. And understanding that chain is how you protect your equipment.
Right. So on this slide, we dive into the heavyweights, igneous rocks.
Oh, yeah. Granite and basalt. Because of how they cool, they require massively high energy crushing. They have huge abrasion resistance and very high uniaxial compressive strength.
UCS, right. Like, how high are we talking?
We're up to 400 megapascals.
Oh, wow. That is massive.
It is. So that mandates heavy-duty jaw crushers for the primary stage and cone crushers for secondary and tertiary, and you absolutely need high-manganese cast steel liners.
Because standard steel would just get destroyed.
Oh, shredded instantly.
So moving to the next slide, we see a stark contrast with sedimentary rocks.
Yeah, night and day. Limestone is basically the forgiving global standard. It has low abrasion, it's easy to crush.
So you don't need the massive jaw crushers.
Not always, no. Impact crushers become highly viable here, which saves a lot of energy.
Wait, let me push back on that for a second. Looking at this slide, sandstone is also sedimentary, but it's listed in a massive danger zone. Why does a single sedimentary quarry suddenly spike in abrasion like that?
That's all about the cement. Sandstone is clastic, meaning it's tiny particles glued together. If that cementing matrix happens to be silica-rich, well, your abrasiveness goes completely off the charts.
So it acts like sandpaper on the machine.
Exactly. You have to test the specific rock, not just trust the sedimentary label.
Got it. Okay, on this slide, we tackle metamorphic rocks and the foliation challenge.
Right, so foliation refers to inherited planes of weakness. Because rocks like gneiss and schist are formed under directional pressure, they have this built-in anisotropy.
And that's a huge threat to the equipment.
It's a threat to your product quality. If you put them in jaw or cone crushers, which use compression, you amplify out of spec flakiness.
Oh, I see. It's like splitting wood along the grain. You don't get nice blocks, you just get these long splinters.
That's a perfect analogy. You end up with highly flaky material that fails spec. The solution is impact crushers.
Because they strike the rock differently.
Yeah, they use repeated strikes in completely random orientations. It basically forces the rock into cubical in-spec fractures.
That makes total sense. So moving to the next slide, we operationalize this data with the wear part threat scale and field testing.
Right, so you have the scale. Low threat is your limestone or gypsum, where standard steel lasts for months. But extreme threat is something like quartzite.
Which just devours wear parts.
Totally devours them. You need heavily profiled specialized parts for that. But you can figure out where you stand with the 10-minute field test triad.
Okay, walk us through that triad.
First, just a visual inspection of the texture. Second, the hardness test. You take a standard steel nail, which is about 5.5 on the Mohs scale. If the rock scratches the nail, you know it's highly abrasive.
And the third step?
The acid test. Drop some 10% hydrochloric acid on it. If you see fizzing, that indicates calcium carbonate, meaning it's likely a softer limestone.
A nail and some acid. That's incredibly practical.
It really is.
So on our final slide, we arrive at the bedrock principle.
The bedrock principle summarizes everything. Geological maps are merely starting points. A quarry that's mapped as limestone might actually contain recrystallized low-grade marble from some ancient thermal event.
So you can't just trust the paperwork.
Never. You must always reverse engineer a rock's crushability right there in the field to configure your chamber correctly.
That is huge, and it leads to a really provocative thought to leave you with today. If the exact same rock can completely destroy one machine, but be perfectly processed by another simply by changing the angle of impact, well, how much energy and steel are we wasting globally right now just by using the wrong mechanical force on the right geological material? Something to think about.